Hello, good morning, good afternoon, and good evening. I'm Lynn Canavan, VP of Marketing for the DDS Foundation, and it's my delight to welcome you to our first webinar for 2024. Today's webinar is going to be a terrific one. It's going to walk through the history of how the DDS standard was started. So without delay, I'm going to talk a little bit about the DDS Foundation, who we are, and then get into today's webinar. So the DDS Foundation was formed to help grow DDS usage across industries. We are collaborative with the object management group DDS SIG, which is the technical body that works on the different specifications for DDS. And we are an open membership group that is open to DDS users, institutions, researchers, universities, and also the DDS vendors. And our mission is really to help promote the adoption, interoperability, and success of DDS across the board. Today's webinar is the first in a series of things that we're doing for this year. This is the 20th year of the DDS standard, and it's 20 years of innovation. The DDS standard continues to be added to and to evolve, and we're really delighted to show all the different aspects of the DDS standard. So look for more events for us. You can find information about it on the OMG or the DDS Foundation website. So with no further ado, let's get into today's presentation. It is being recorded, so if you like what you hear, please feel free to forward this on to your colleagues to listen to the replay. There will be a Q&A at the end. We have permission to run a little bit over, so the presentation itself will take about 30 minutes, and please add questions into the portal, and we'll get to them at the end of the talk. So with no further ado, I'd like to introduce today's speakers. Mark Swick is joining us, and he is the person who worked on the original spec, or the original the original work that was looking at the project to form the DDS standard, what the technologies were, what the Navy needed. And he is joined today with Gerardo Pardo, who is one of the lead authors of the DDS specification and RTPS specification. So both of them are here today, and let me go ahead and turn it over to Mark.
Thanks, Lynn. So I'm going to go back to the 1970s and 1980s, a really long time ago. Surface ships and submarines have had fire control needs since World War II, basically. They were a lot more manual then, but computing has always been part of the problem set especially for fire control on surface ships. They have multiple sensors, multiple shooters, and it's been that way since the 70s. And the Navy's been doing distributed computing in that realm since that time. And it could be done on surface ships and submarines because they had sufficient power from nuclear generators and sufficient size to bear the weight of the computing machines that were available at that time. Some of their needs included fault tolerance, right? We had to build systems with no single points of failure. So you had to have built-in redundancy, and you had to have graceful failure. In order to shoot at something, you also needed determinism. You needed to have this dance between the environment around you, multiple set data from multiple sensors, and then choosing and applying your decision to the thing you wanted to shoot at something with. And of course, as we progress to threats coming from ships and shells to missiles and jet aircraft, all this had to be faster, and faster than humans could do on their own. So the computing became very important. This picture is a Yuck 7 cluster of computers actually from a submarine. And you see all the cables on top of these computers. That was the network at the time, and the weight of the cables for each of these channels actually figured into the ballast of the ship in terms of where these cables were run and where they were placed. So, in terms of power and weight, the needs were massive at that time. These were core memory computers. We were doing fire control in 256K at that time, but you still needed the redundancy, the determinism. But these physical constraints greatly limited your ability to scale and to maintain systems. It was extraordinarily expensive to do this. So this was what was being deployed around 1980. And this first ship I actually worked on was the USS Virginia. It was a nuclear-powered cruiser. solving this problem. And the great advance was going from core memory to semiconductor memory. This picture is an AN-43. But again, we're talking about less than a meg of total memory, and doing fire control and multi-sensor integration. So it was a challenge, and it was a very expensive challenge because the Navy was paying for its own hardware, its own software and language. And this was all around something called NTDS, or Naval Tactical Data System. That described the messages going over those wires and how the computers interoperated. Now, in the transition, meanwhile, industry is changing rapidly, right? With Moore's Law, we're having this great advance in computing speeds. And then with the advent of basically 100 megabit Ethernet became the transition point at which we could move this distributed communication off the wires and into commercial networks. But a lot of people didn't believe it could be done. There was no proof that you could meet the needs and the timing needs of these systems with commercial hardware and commercial networks. So the Navy needed hard data on that. That led to, in the mid-90s, the beginning of a series of experiments called the Hyper-D, or High Performance Distributed Computing experiments. This was in the context of a large-scale prototype of a naval combat system using commercial equipment. Now, we started with a massively parallel computer with actually it was a Paragon Intel computer, with the idea that if you had enough computing power, you could solve this problem. Of course, the problem turned out to be a distributed computing problem, because you couldn't get enough data in and out of this box with existing network technology in order to solve the problem. So we actually ended up just creating and implementing a distributed reference architecture that provided the determinism and high availability and fault tolerance that was needed to meet these requirements. And as part of this evaluation, we looked at a variety of computers, everything from Sparks to Intels to PowerPCs to custom computers, a wide range of operating systems. Of course, Linux, the entry of Linux was a game changer in that, and having an openly available, near real-time operating system was a big thing. But we used HPUX, we used DEC operating systems, all interoperating together. Multiple languages. There was a need for Java for display. C was becoming more mature for the real-time side of things. We had multiple networks. It wasn't clear at that time that Ethernet was going to be the network. There was ATM, there was FDDI, there was MirNet. There were multiple network combinations to try. But we tried to basically do apples and apples comparisons across all these things. And of course, middleware made it affordable to do these things, because we in order to do these evaluations with a small team, we needed portability and interoperability in order to conduct these experiments. The other big thing is that we instrumented these experiments in real time, so we could run an experiment and immediately get feedback on whether we were meeting the latency and performance and determinism requirements of the system. So as a result of this, the Navy realized that open standards was a key to being able to make this affordable. They didn't want to build their own computers. And in fact, at one time, the Navy tried specifying the hardware, specific hardware to be used, even though it was commercial hardware, and thinking that was open. Of course, by the time they made the decision and the selection about which specific hardware, and it was HP at that time, they were going to use, everything they had selected was already obsolete, as you saw from the graph earlier. So it became clear that the only way to migrate and take advantage of ever-increasing commercially available components was to dedicate yourself to open standards, and portability and interoperability. Those were going to be absolutely key. Now, in terms of the requirements for throughput and determinism, we evaluated a number of things, and it turned out that first among those was a splice from Thales Naval Netherlands, and which was used in the Tacticos control system on Dutch ships, and RTI NDDS, which was a key part of that experiment infrastructure. These were proprietary products, of course, at that time. And we looked at other proprietary products as well. again, the needs, so fault tolerance and determinism, as I mentioned before, were key. Those had to be met first, right? But given the changing landscape of available hardware and software, scalability became another key requirement, right? Now we could add, you could add and remove capability dynamically in order to meet changing threats, which became a key requirement. And maintainability and lifecycle, which was so very difficult in the past with all custom hardware, software, and even computing languages. It became clear that open composable architecture was really a requirement in order for things to be affordable. And you needed adaptability across operating systems, CPUs, networks, languages, and middleware. As I said, the mandate approach with Ada and with HP and with other things proved to be not sustainable and didn't work. And the path to get there was open standards. Now, the CSAR project coming out of joint computing from the Navy, MITRE was a big part of this, contributed to that. Also emerging robotic and space systems. Of course, NDDS came out of the Stanford Robotics Lab. ESA and NASA also were contributors and had needs in this space. And more complex automation systems, launch control at KSC and Schneider Electric, all were early adopters and recognized the need for this capability to adapt to a changing hardware and software world in order to have affordable systems. Other things that we looked at in the Hyper-D experiments included Corba and Java RMI, and those found their ways into these systems, but mostly migrated out over time. RPCs and client server introduced strict coupling. Any kind of one-to-many communication was very difficult. In fact, in Corba, they invented an event service and a notification service, which were just too tedious. They weren't naturally many-to-many communication patterns, which was ultimately what was needed. Message queuing from IBM and Microsoft were primarily proprietary. They were all TCP-based, as Corba was. A series of experiments done at Dahlgren proved that TCP simply isn't suitable in terms of being able to bound the latency sufficiently to get the determinism required over a long period of time, remembering that these are 24/7 systems that we're talking about. Service-oriented solutions, again, higher latency, server broker-based, single points of failure, deployment, required enterprise hardware, and just couldn't meet the real-time requirements. And then there were other pub subs out there which were evaluated. They were either proprietary or broker-based and had no interest in moving to an open standard, most importantly. So with that, the characteristics of Splice and NDDS were both found to be extremely valuable to the Navy. And RTI and Thales, the Navy with MITRE, entered into this discussion to create a standard which embodied the key features of both of those products in an open standard going forward. And it really was a successful meeting of minds that resulted in the initial DDS standard, whose whole purpose was to standardize these interfaces and behaviors to get us portability and then later, of course, interoperability. And with that, I'm going to hand the presentation over to Gerardo, who is, of course, as CTO of RTI, was really the key driver behind the creation of the standard.
Right. Thank you, Mark. So yeah, so a little bit of, like Mark said, I think at the time, we had the product called NDDS, and similarly, Thales had a product called Splice, and we had actually talked to each other and realized that while these products were having a reasonable amount of success in the market, what people really wanted was a standard, right? People didn't want to go to a proprietary technology. People wanted to have a choice of vendors and the guarantee that if a vendor went away, they could just find a different vendor. So so we actually talked about how we could come together and create this standard. We tried different organizations and eventually converged in the Object Management Group, which was the organization that had a very successful standard at the time, which was Corba. So it was doing good work in middleware standards, and we felt that that was the right place. And the Navy was very involved in that organization, so they were also nudging both of us, Thales and RTI, to join and contribute our technology there. So in fact, so you can think of DDS as being kind of like the merging of these technologies and the ideas and the evolution of them. And in fact, in the first version of the specification, this sentence appears that says that really what DDS tried to accomplish is define standardized interfaces that essentially provided the capabilities that these technologies had already proven in different markets. So just to roll back why this was important, we were seeing the need a little bit broader than just the Navy type systems. It's no surprise that kind of defense is always a little bit ahead of others because they have sort of the more stringent and demanding needs. For example, the internet we know came out of a defense initiative, DARPA, right? So they were a little bit ahead, but since on our side we had been working at Stanford and working a lot with NASA, and they had similarly fairly complex robotic systems, and some of the industrial automation people that were also looking at complex systems were already asking for this kind of publish subscribe technology that could give you sort of a modular architecture that had sort of maximum performance, maximum scalability, and the best sort of real-time characteristics, as good as the underlying hardware and networks could provide, right? So in these markets, supporting real-time, low latency was kind of like a must-have. I put here a quote I heard once from a Navy admiral that said, I don't know what real-time really is, but I know what not real-time is. And not real-time is when they shoot at you 22 missiles and you can only shoot down 21, right? So you didn't meet your deadline, and that's a bad thing. But beyond determinism, there is also this notion of non-stop operation that Mark alluded to. You can't stop the real world, right? So it means that you cannot stop your software. Your software has to continually make decisions. And if something fails, well, you have to figure out what to do with whatever is still operational. So this is very different from transactional type systems. Like you can think of like a stock exchange. Well, they operate during the daytime and then they can shut down their systems in the evenings, right? Or even, if there is a failure in the day, sometimes they stop the stock market, right? And say, okay, we'll stop the stock market. We figure out what things happen and then restart. And yeah, people get upset because they cannot do the transactions, but there is no sort of fatal consequences out of that. But in a system that is kind of controlling hardware, like, an air traffic control system where flights are coming and they're trying to land, well, you can't just suspend time, right? The flight is coming and they're landing or not landing, and they have to make a decision instantaneously. They cannot just kind of freeze in the air. And so this is why, people like the Navy and CESAR, which was the air traffic authority from Europe, trying to unify all the different air traffic control systems in Europe, as well as robotics and launch control from NASA, which is again a very sort of time-sensitive decision. Where you're launching a rocket, you have a certain amount of time to make a decision to launch or not. You have to check out that everything is healthy and then go, no go, right? So these kind of situations were the things that were driving the need for a different kind of technology, something that was targeting more the real-time systems than the sort of banking transaction type systems that message queues were targeting. And then in the end, like Mark said, people were moving to commercial hardware, commercial networks, and so on, use of different programming language. So it's really important that whatever you create can actually be deployed on top of all these different technologies. It's not tied to like, oh, well, you have to run on top of like a shared memory or kind of a reflective bus or something like that. No, it has to run on top of whichever hardware you choose to deploy it, because you know that the hardware is going to be evolving very fast, in a lot of times faster than the protocols and the applications. So therefore, you have to be able to kind of take advantage of those technologies as they come about. So in the end, what really happened was that RTI with Thales, we joined in the object management group, and we sort of created sort of a specific a draft specification, and we had stakeholders from the Navy, from CESAR, from MITRE, sort of contributing the requirements and reviewing them. And then the whole process organized by the OMG, where they have a fairly good governance of reviews. People in the community can join, vote based on the specifications, provide feedback on the drafts. So we had very active participation from companies like Raytheon, Selex, and so on, which were kind of end users of this technology. And the joint work of this came out with what I would think are the two main specifications. The two first, at least, that came out were the 2004 DDS specification and the 2006 RTPS specification. So the DDS specification is about the programming model, the publish subscribe, what we call the data-centric qualities of services, and so on. So it gives you a level of portability. And the RTPS, or real-time publish subscribe, is the sort of wide protocol interoperability that allows two applications that are built potentially with different middleware stacks and in different programming languages or operating systems and what have you, to actually communicate on the wire with each other. So here we have the pictures of the people that contributed to the original standard. So we've got Virginie in the middle from Thales, and Hans Van Haag also from Thales, and myself from Real Time Innovations. MITRE with Char Wells was kind of like the main reviewer of the specification from the government side, as well as all the other companies that I mentioned. So these DDS and RTPS were the two first specifications, and what they actually provided was sort of this concept of a shared databus. A shared databus being a space where applications can essentially publish and subscribe information, and they do it in what's called a data-centric way, meaning that what they publish are sort of data objects, and those data objects exist in this global data space, and applications can essentially update them, and other applications can subscribe to them. And you can have multiple objects of the same topic coexisting. For example, if you've got, in this example, a bunch of turbines, each one publishing their state, the different turbines have an identifier that essentially makes them separate in their life cycle. So it's very similar to a relational model of databases where you've got records, and these records are in tables, and you can update each record separately, except there is no essentially disk in between. Applications are communicating directly peer-to-peer without any brokers. And that was really like sort of the big innovation that came out of the data distribution service specification, the idea of a publish subscribe data-centric model that use QoS to get applications to be able to communicate peer-to-peer. So of course, that was the beginning, 2004, 2006, but there is now a lot of specifications that come out of this family. And there are specifications that address sort of the modularity aspect and the architecture aspects, like DDS, of course, was the first, and now we're in version 1.4 of that specification. But there are other specifications, for example, X types, that describes the type system. What are the types that you can publish and subscribe? How are they serialized in the wire? How do you change and evolve your data types without breaking interoperability between applications? So you can have an application deployed with a version of the type, and then you can change to a new version of the type, and those two applications can still communicate, even though the types are not exactly the same. Then there are specifications that talk about quality of service and how to define profiles, so you can very easily define a system architecture with DDS XML, and even like a specification that allows you to do sort of an RPC request reply type of pattern, but a sort of a brokerless, kind of serverless RPC that is loosely coupled. So this is kind of the architecture specifications. Then we have specifications that address how to program that from different programming languages, from C++, Java, C#, and so on, that provide portability. And then the very important aspect of application interoperability, which comes from the RTPS real-time publish subscribe specification, now in version 2.5, and even some recently adopted specification, TSN, that describes how to deploy these systems on top of TSN, which stands for time-sensitive network, which is a recent standard that allows the use of commercial Ethernet hardware to do real-time communications on the Ethernet. And of course, with the time, security became a very important consideration. So a security specification was defined about 10 years ago, and now we're on version 1.2 of the specification, addressing all these sort of concerns in a peer-to-peer data-centric secure environment. So like Lynn said, this has been 20 years of innovation. We started in 2004 with the first DDS specification. We're now 2024, and we're still working on a specification. We just released a DDS TSN that I just mentioned. We're working currently on a DDS monitoring specification, and in between are a lot of the specifications I mentioned, and some I didn't have time to talk about. And from the early companies that worked in the first specification, RTI, Thales, MITRE, and the stakeholders like Navy, to the rest of the companies that joined, new vendors implementing the specification that joined later and were able to now participate and create new specifications and revise the existing specifications. We have a very vibrant and an active ecosystem of companies working together to evolve all this and to meet the market needs and to meet the evolving technology landscape. So today, I don't have time to go through this, but this slide describes all the specifications that are part of the DDS family and how they fit together. So we have the DDS core specification, the programming languages, APIs on top, the RTPS, real-time publish subscribe protocol underlying, and then a number of additions that allow you to define the type system, security, request reply, communications over low bandwidth networks, integration with other technologies like web services, REST, OPC UA, and so on. Now, the next step for DDS has been the adoption of DDS as a technology by a set of other organizations that are themselves building their own standards. So it's kind of like standards built on top of other standards, just like DDS was built on top of things like UDP, TCP, which are standards at the network level. Well, there are other companies and organizations that are building the standards that layer on top of DDS as a standard. So we've got in a lot of different domains like defense, automotive, healthcare, robotics, power, whole organizations that are saying, well, we're going to create something that is dedicated to our needs, but it uses DDS as the underlying foundation for communications, data modeling, QoS, configurability, discovery, and security. So, and today, these systems that are using DDS are deployed everywhere. There are literally thousands of systems out on the network, very large systems, aerospace type systems, planes, automotive, launch control systems, trains, healthcare, robotic systems, really in every domain that has sort of complex real-time or complex high availability requirements where latency is important, where determinism, where availability is important, you really can find an application of DDS. So with that, I'd like to conclude my presentation.
All right. Thank you. Thank you so much, Mark, and thank you so much for Gerardo. So Albert Einstein once said that if you really want to know the future, you really have to look at the past. So again, we are looking at 20 years and going strong of DDS. And I think that this is a really terrific stroll down memory lane to see where it was, where it began and what the fundamental aspects and needs were for the DDS standard. Mark and Gerardo, you both have been involved with DDS for 20 plus years. And I wanted to just see if you could share a highlight, something in particular that stood out for you of, a good moment for you with DDS, something that, I'm sure there were many over those years, but if you wanted to let us know, what was a particular highlight for you? Mark, maybe you go first.
Sure. So I guess in November of last year, we had the Artemis 1 launch. It was a rocket from KSC, which circled the moon and tested the Orion capsule, which will be carrying humans to the moon in the next year. Having worked with KSC on this system for over 10 years, and given the criticality of DDS to the system, in which all the data moved to all of the launch control operators was moved there using DDS. They had me sit at an operator console for the actual launch, and that was a true career highlight for me.
Yeah, I think if you talk about a critical real-time system, that's certainly a space launch is really at ground zero on
Well,
that.
it was a little terrifying because if they had lost one update out of 500,000 updates per second, the launch would have been scrubbed. So it was kind of a hot seat at the same time, but very rewarding.
And they did not lose it. So
no, it was a totally successful launch. Yeah.
Because that's a situation, I've talked to Mark about that, that's a situation where they actually use like best effort communications, but they actually don't expect to lose any data, right? They use best effort because of the lower latency. But if they lose any data, they're like, oh, wait a minute, this is not good enough. We can launch.
Right. So actually, we use a form of reliability called negative acknowledgement only reliability that turned out to serve them very well.
Uh-huh. Yeah, for me, I would say, having worked a lot on the standards, it was very good experience when more companies started joining the ONG, and all of a sudden they would come and say, hey, we've been watching this, we've been reading the specifications when we actually implemented the specification, and we want to come here and show that our technology actually interoperates, and we would try, do some interoperability tests, and lo and behold, these things would work from the get-go. And would like, well, I had not expected that people would be able to actually do that just reading the specification without ever asking any questions or providing any indication they were working on it. So it was a very pleasant sort of surprise and sort of an endorsement of the thoroughness of the OMG process that kind of ensures that specifications are sufficiently well clear and thorough that people can follow them without being an active participant on the development of the specification.
Yeah, that's terrific. That interoperability. I think that again, that's the reason for the standard, which is terrific. Okay, so again, for questions, please submit them. There is a question. It's a little technical, so bear with me while I read it. It is, can you explain how any sensor, any shooter, is realizable in a federated system of multiple platforms with wireless, low bandwidth, BLAWs, connections in a contested EM environment, and how that can be implemented using DDS?
Well, I can take that one because it already has. There is Northrop Grumman has developed a system which has gone to production for the Army called the Integrated Battle Command System, or IBCS. You can Google that and get to the Northrop Grumman site and get the information on that. So yeah, that's something that's actually already been done using DDS.
Okay.
I mean, DDS is not going to do something that is not possible with the underlying hardware, right? So I think that the trick here is that you don't want to be worse. You don't want to add to the problems that you may have. Like a packet could be lost because the user is contested, wireless networks. So there could be noise injected and some packets could be lost, right? Now, you could just send another packet, right? But if you have the wrong protocol, like a TCP type thing, which tries to queue every message, and all of us say, well, I lost this thing, and now I need to send all these other things that were sent after that need to arrive before the next byte can be sent. So you have no flexibility on sort of saying, okay, drop that, and let's here, get the most recent data as the most critical one, and overcome that glitch as fast as possible with the minimum disruption to the system, right? So the key of DDS is by having these protocols with quality of service and by deploying peer-to-peer type of technologies, we're not adding anything to the underlying infrastructure. So if you've got an infrastructure, yeah, it can have packet loss. We can recover from the packet loss. We're not going to make it worse. We're going to let you exploit that capability to its full extent and give you the best recovery that you can have.
That's exactly right. I mean, you can bound the latency associated with reliability. Reliability and determinism are in tension naturally. And DDS allows you to resolve that in a manner that allows your system to continue to operate even in challenging environments.
Yeah. For DDS, reliability is not an absolute, right? When people think about reliability, they think about TCP reliability where every byte has to be received, right? In the same order that you send. And for DDS, reliability is a continuum that is controlled by a quality of service, where you realize that you've got many parallel streams of information with many topics. You're talking about many objects for each topic. So, for example, a radar track system is sending you track data on a single topic, but there is many different tracks because it's tracking many different things, right? Some of them may be moving faster than others, right? And every single update may send you an update of a specific track. And reliability could mean give me the most critical track first. Give me the latest data of every track before you try to give me a data that is like 10 seconds old, because that may be less important, right? So with quality of service, you can configure what you want to do. You want to like queue things. You want to prioritize the latest data over the earliest data. Do you want to drop data that is already too old? Maybe after a few seconds, that data is really not important and you don't want to be filling your queues, right? That's the kind of thing that DDS provides you with the quality of service that you cannot do with other middlewares that were kind of had a more like transactional perspective on what the application would look like.
Okay. All right. Thanks. Hopefully that answered the question, and the person who submitted it, if it didn't, please type in anything, add on into the chat. Okay. So the next question is there an impact of the Unified Architecture Framework, the UAF development on DDS?
Mark, do you want to take that, or do you want me to?
Well, and DDS fits into lots of architecture frameworks. And there's been multiple DODAF and MODAF programs that use DDS as part of their implementation. How it's expressed in their models varies, right? But there's no real impact that I can see with that. Gerardo, you may want to add to that. But.
Right. I mean, I think so as people are moving more to model-driven type of architecture, right? So like the impact would be like, well, how do you express this type of considerations in a model-driven architecture, and how you take advantage of that? So I mean, there are extensions, and there is work that has been done with a specific, vendors of SysML technologies and MODAF and TODAF type technologies. Is something that there was a very early on standard on it, but the technology evolved so quickly that standard never actually materialized. By the time people were trying to implement that, SysML had evolved and those technologies had evolved. So I think right now the impact is more at the tooling level, like people are building those as tooling extensions, and they are taking into consideration the data-centric sort of architecture from the get-go, right? To the extent that there are architecture like Phase that are based on this. But there is no, at the standard level, there is nothing really there. Maybe it's something that would be worth, it's never a stop, right? We've been creating a standard, so it would be another one that maybe should be prioritized in the community.
Okay.
But, DDS has been part of those kind of tools for many, many years, going all the way back to Rhapsody.
Okay. All right. Thank you. I'm going to ask one last question, which is, okay, so we 20 years ago, there was, one big customer or one big user that was looking for this. It's certainly expanded and been deployed in thousands of other, use cases and projects over the years. Where would you like to see DDS going, or what do you see coming next? What is your hope for the DDS standard in 20 years from now, when we're looking at 40 years of DDS? What will you say? Wow, that second 20, the second part of the journey. This is where we really did something.
So I think, really, like, the technology is evolving, right? And I think the realization that sort of dependability and real time and sort of peer-to-peer architectures around a publish subscribe are a critical component. I think where I see DDS is basically becoming sort of the foundational, programming paradigm for these types of systems. Very similar to how, in the kind of web world, like REST eventually has taken over, right? There was a lot of like discussion early on, should you do like SOAP and like service over this, but in the end they went back to like sort of the REST protocol. Their state transfer is more scalable and so on. So I think we've seen a lot of things in the sort of real-time world, a lot of different technologies, but over time, I think over time I see people converging around building their application on top of sort of a data-centric architecture. And like we've seen a lot of standards out there building on top of DDS as a foundation. So I think we're going to see more of that, and essentially see the world sort of divided into these kind of two stages, like the more like cloud-based transactional world for analytics and so on, and the more like peer-to-peer sort of real-time for kind of edge autonomy, edge AI, edge control type systems.
Yeah. Over the years, things move from the cloud to the edge and back. That's been going on for a long time. But the communication needs are pretty much the same. And determinism, for example, as Gerardo mentioned earlier, determinism and reliability are always going to be in tension. Scalability and determinism are going to be in tension. These are things that DDS helps resolve that really no other communication technology, even after 20 years, addresses those critical needs.
Okay. All right, great. We're going to take one last question that has come in, and apologies if I'm mispronouncing this, but it says, does DDS play nice with K8S, even multi-cloud K8S with comms between clusters? I imagine that's an acronym for something. Apologies for not knowing what that is.
I think that's talking about Kubernetes, I would assume.
Okay.
Yes, so containers, right, and Kubernetes are deployment technology. So, I mean, it plays nice, but it could play nicer. That would be my sort of analysis. I think in the so Kubernetes by itself, it's fine, but typically those networks, there is a set of overlay networks that come along, and depending on which network technology you are using, some of these network technologies may be trying to do too much for your own good in the case of real-time applications, right? They may be trying to say, well, we're going to do like some kind of VPN for you, or we're going to try to like centralize everything, or we're going to try to run everything over TCP as opposed to let you run, multicast or UDP. So to the extent that those overlays try to do things that are not good for real time is problematic, but it's not really a problem with Kubernetes itself. It's more of a problem of the, infrastructure that may be built around these technologies without realizing that, that there are needs for applications that are more like deterministic than the typical applications that started this whole thing in the cloud. But yeah, we have a lot of systems deployed with containers and Kubernetes, and it's possible to do if you pick the right technology stack.
Okay. Great. And actually, so if you go to the DDS Foundation website under some of the past presentations and some of the resources, we had a very nice presentation by a PhD candidate at Vanderbilt University on Kubernetes working with DDS. So I invite you to look at that as well as look at the other resources from the DDS Foundation on DDS. So I wanted to conclude today's webinar and thank our two speakers very much for this great walk down memory lane. Again, thank you so much to Mark and to Gerardo, and thank you all for joining us today. And look forward to the rollout of the rest of the year for the 20 years of innovation celebration of the DDS standard. With that, I'm going to conclude today's call. Thank you very much for attending.